Hello, am I audible? Hello,
Yes, sir. Hello.
hello, am I audible?
Yes, sir.
Okay, so today we'll discuss the statistical thermodynamics 2. So here in this part, first we'll discuss the Boltzmann's distribution. So what is that? In a system containing many molecules, the variable quantized energy states are occupied by different fractions of molecule. That means if a system, a large number of different types of molecules are there, then the quantized energy levels are occupied by different fractions of molecules. Suppose out of the 100% of molecules, different percentage of molecules are present in different quantized energy levels. This is the entire population of molecules. That is, the entire population of molecules are occupied by entire population of molecules is distributed among the different energy states. Alternatively, we can say that the total energy of the system is distributed amongst the constituent molecules. Now, Boltzmann was the first person to propose an expression to calculate the population of different energy states. So that means different energy levels are there. In every energy level, how many molecules will present? That is known as population of energy levels. In every energy levels, how many molecules are present out of a large number of molecules. So that was proposed by Boltzmann. So this expression is known as Boltzmann distribution function and is essentially a probability distribution function that allows to calculate the probability of finding the system of a certain energy state. Now, before going to discussion in details about the Boltzmann distribution function, first we should know that what are the different types of microstates and configurations. Microstates and configurations. So here, let us take a sample molecular system containing three quantum particles that collectively have an energy equal to say 3 quanta. Again, I am repeating. Let us take a simple molecular system consisting three quantum particles that collectively have an energy equals to 3 quanta. The energy states available for the particles have energies. The energy states available for the particle have the energy. So each particle having the energy state, this is the ground state energy level, that is 0, then epsilon 0, then 2 epsilon 0, then 3 epsilon 0. So these are the energy states available for the particles and so on. Where epsilon 0 represent a quantum energy. Now we ask a question, what is the most probable distribution of energy? That is, what is the most likely way in which the total energy, so here the total energy will be 3 quanta. So what is the most likely way to distribute the 3 quanta, to distribute the 3 quanta among the particles of the system? To begin with, we assume that the particles are indistinguishable. That means here we will consider that the all the particles are identical. That means we cannot distinguish the individual particles, so the particles are indistinguishable, and try to work out possible distribution. There are three possibilities as shown in the figure. So here in this figure, three possibilities are there. The total energy should be 3 quanta. Here, so these are the energy levels of individual atoms or individual particles. So the ground state, so this is the ground state 0, then epsilon 0, then 2 epsilon 0, then 3 epsilon 0, etc. But the overall energy should be 3 epsilon 0, that is 3 quanta. So there are three possibilities as shown in the figure, and the figure, the first case, in the first case, all the molecules are in epsilon 0 state. So here in the first case, all the molecules are in the epsilon 0 state, having energy equals to 1 quanta each, and hence the total energy will become 3 quanta. And in the second case, the levels corresponding to the energies for the three different molecules. For the first molecule, it will be 0. For the second molecule, it will be epsilon 0. For the third molecule, it will be 2 epsilon 0. And the total energy of the system will become 3 epsilon 0, that is 3 quanta. And similarly, in the third figure, in the third case, the energy with one molecule is in the state energy is 3 quanta. So here, so the energy of one molecule is in the 3 quanta, that is 3 epsilon 0, and the energy of the remaining two molecules is in 0 state. So these are the three possible configurations of distribution of 3 quanta of energy among the three identical particles. Thus we say, thus we see in the above example, there are three different ways of arranging three particles or three molecules in various energy states, such that the total energy of the system should be 3 epsilon 0 or 3 quanta. Again I am repeating. So from this example we see that there are three different ways of arranging three particles in various energy levels or various energy states, such that the total energy of the system will be 3 epsilon 0 or 3 quanta. Such arrangements of molecules in different energy states are called as configuration. You may note that here we have assumed that the molecules are indistinguishable as indicated by their color. Let us take one more example. So here we will discuss another example. Consider a system consisting of 5 identical particles, that means 5 indistinguishable particles. So here n equals to 5, which can occupy any one of the available energy, which can occupy any of the available energy levels having energy equals to epsilon 0, 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, and 5 epsilon 0. If the total energy of the system should be 10 epsilon 0, then identify the different possible ways in which the molecules can occupy the various energy states. So here total 5 identical particles are there, and the different available energy levels are epsilon 2 epsilon 0, 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, and 5 epsilon 0. And the total energy of the system, that means the summation of the total energy of the 5 particles should be equals to 10 epsilon 0. Then the question is, identify the different possible ways in which the molecules can occupy the various energy levels. So here, in this case also, there are several constraints, such as the total energy of the system is fixed. So one condition is that the total energy level of the system is fixed, that is 10 epsilon 0. And the total number of molecules cannot change, that is also fixed, that is the total number of molecules are 5. And the available energy levels are also fixed. The available energy levels are epsilon 0, 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, 5 epsilon 0. That means the available, so there are 5 different available energy levels. Based on these conditions, there are 6 different ways of arranging the 5 particles so that the total energy of the system should be 10 epsilon 0. That means there are 6 configurations. So the different possible ways distributing the 5 identical molecules in the available energy states are given in this figure. So these are the 6 configurations. For each configuration, you can see the total energy of the 5 particles will be equals to 10 epsilon 0. So in the first arrangement, you can put all the 5 molecules in the energy level of 2 epsilon 0. So the total energy will become 10 epsilon 0. In the second configurations, you can see 3 molecules will present in the energy level of 2 epsilon 0. Then total that will become 6 epsilon 0, and another one molecule will present in 3 epsilon 0. So again that will become 9 epsilon 0, and the fifth molecule will present in epsilon 0. So the total energy will become 10 epsilon 0. So this is in the second configuration. So similarly, in the third configuration, if you add the total energy of the 5 molecules, that will become 10 epsilon 0. And similarly, for the fourth configuration, for the fifth configuration, and also for the sixth configuration. So these are the only 6 ways of arranging the 5 molecules in the 5 different energy levels, having energy epsilon 0 for first energy level, to epsilon 0 for second energy level, 3 epsilon 0 for third energy level, 4 epsilon 0 for fourth energy level, and 5 epsilon 0 for fifth energy level, so that the total energy of the system will become 10 epsilon 0. Let us see what happens if the molecules are distinguishable. So in this condition, we are so one condition is there, all the 5 molecules are indistinguishable. That means all the 5 molecules are identical. So you cannot distinguish individual molecules. But in the second case, in the next case, so here let us see what happens if the molecules are distinguishable. So, when the distinguishable objects are distributed into separate subsystems, there are more possible ways of doing so as compared to that of the indistinguishable objects. So, if indistinguishable objects are there, so the number of possible ways will be less. But if distinguishable objects are there, so to arrange them in the different energy level, more possible arrangement will be there. So that we will see. In such cases, each configuration can have one or more than one permutation possible. Now, let us consider the example of distribution of 3 quanta of energy. Let us consider the example of distribution of 3 quanta of energy. So here in the if the particles will be indistinguishable, we have discussed 2 different examples. So for the same 2 different examples, again we will discuss what are the different types of configurations if the particles are distinguishable. Let us consider the examples of distribution of 3 quanta of energy among the 3 particles discussed in the above case. But now we will take one condition that all the particles are distinguishable. That means all the particles are separate. We find that the 3 configurations are identical for each case with indistinguishable particles that can one or more permutation are shown in the figure 4.2. So here this is the figure 4.2. So in this figure 4.2, we have to arrange 3 different molecules in 4 energy levels, having energies. The first energy level, the energy of the first energy level is 0. The energy of the second energy level is the energy of the first energy level is 0. The energy of the second energy level is epsilon 0. The energy of the third energy level is 2 epsilon 0, and the energy of the fourth energy level, that is 3 epsilon 0. So here these are the 4 energy levels, and 3 particles are there. The 3 particles are distinguishable particles. One will be in the red color particle, and another one is green color, and another one is blue color particle. So here these are the 3 distinguishable particles, and we have to arrange the 3 distinguishable particles in the 4 possible energy levels, so that the total energy levels of the system, so that the total energy of the system will become 3 quanta. Now, what are the different combinations? So here, as the particles are distinguishable, the number of combinations will be more. But in case of indistinguishable particles, the number of combinations will be 3 combinations will be possible, so that the total energy of the system will become 3 quanta or 3 epsilon 0. But here, as the particles are indistinguishable, large number of combinations are possible. So here the different combinations we can see. So in the configuration number 1, all the 3 particles will present in the energy level epsilon 0, so that the total energy of the system will become 3 epsilon 0. In the configuration number 2, the red particle will present in energy level 0, the green particle will present in energy level epsilon 0, and the blue particle will present in energy level 2 epsilon 0, so that the total energy level of the system will become 3 epsilon 0. And similarly, in the next, so this is the configuration, the microstate of the configuration 1. So in configuration 1, you will find one microstate. But in configuration 2, the configuration 1 is like that. In the configuration 1, you have to put all the three particles in a particular energy level, that is epsilon 0, so that the total energy of the system will become 3 epsilon 0. The configuration number 2 is you have to put one particle at 0 energy level, one particle at epsilon 0 energy level, and another particle at 2 epsilon 0 energy level, so that the total energy of the system will become 3 epsilon 0. So that is the configuration 2. So here in the configuration 2, large number of microstates are there, because all the three particles are indistinguishable. As the three particles are indistinguishable, in the configuration 2, there are 6 microstates are there. Because the particles are distinguishable, so in configuration 2, 6 microstates are there. But if the particles will be indistinguishable, only one microstate will be there in configuration 2, and one, so that we have already discussed. So here the particles are distinguishable, that is the particles are distinguished as one particle will be red color, another particle will be green color, and another particle will be blue color. So arranging them in three different energy levels, having energy 0, epsilon 0, and 2 epsilon 0, 6 microstates are possible. So in the first microstate, you can see in the first microstate, the red color particle will present in 0 energy level. The green color particle will present in epsilon 0 energy level. The blue color particle will present in 2 epsilon 0 energy level. Similarly, in the second microstate, the red color will present in 0 energy level. The green color will present in 2 epsilon 0 energy level. The blue color will present in epsilon 0 energy level. In the third microstate, the red color will present in epsilon 0 energy level. The green will present in 0 energy level. The blue will present in 2 epsilon 0 energy level. And in the fourth microstate, the red will present in 2 epsilon 0 energy level, the green will present in 0 energy level, the blue will present in 2 epsilon 0, the blue will present in epsilon 0 energy level. In the fifth microstate, the red will present in epsilon 0 energy level, the green will present in 2 epsilon 0 energy level, and the blue color particle will present in 0 energy level. And in the sixth microstate, the red color particle will present in 2 epsilon 0 energy level, the green color particle will present in epsilon 0 energy level, and the blue color particle will present in 0 energy level. 0 energy level. So all these three microstates, you will see that the total energy will become the epsilon 0, and in all the three states, you can see one particle will present, whether that may be red, green, or blue color, one particle will present in 0 energy level, and another particle will present in epsilon 0 energy level, and another particle will present in 2 epsilon 0 energy level. So there will be 6 microstates are there for configuration number 2. Now coming to the configuration number 3. So in the configuration number 3, you have to arrange the 3 particles so that 2 particles will present in 0 energy level, and 1 particle will present in 3 epsilon 0 energy level, so that the total energy of the system will become 3 epsilon 0. So the two particles which are present in the 0 energy levels are green and red color, and the one particle will present at 3 epsilon 0 energy level will be blue color, that is called microstate 1. And in microstate 2, the two particles that are present in the 0 energy levels will be green and blue color, and one particle will present in 3 epsilon 0 energy level will be green color particle. And in microstate 3, the particle which is present at 3 epsilon 0 energy level is the red color particle, and the two other particles that are the blue and green color particles will present in the 0 energy level. So in the configuration number 3, 3 microstates are possible. So there are total number of microstates will be 10. So here the configuration, so 3 configurations are there, but the number of microstates will be 10. The configuration and the corresponding microstates for the distribution of 3 quanta of energy among the 3 distinguishable particles. So here coming to this, the distinguishability of the particle is indicated in the color, in the term of the color of the spheres representing the particles. The configuration 1, 2, 3 have 1, 6, and 3 permutations respectively as shown in the figure. The specific arrangement, that is the permutation of the particle in a configuration, is known as microstate. In other words, we can say that a microstate is equivalent to permutation in probability theory. And here a configuration in the case represented as N0, N1, N2 and N3, where N0, N1, N2, N3 refers to the number of particles in the energy states. So here we are discussing in the second case, that is 5 particles are there, and that should be arranged in the different energy level. So here in the case, the configuration in this case is so represented as N0, N1, N2, N3, where N0, N1, N2 and N3 represent the number of particles in the energy state 0, epsilon 0, 2 epsilon 0 and 3 epsilon 0 respectively. That is, 3 configurations given above will be represented as 0, 3, 0, 0. That means all the 3 particles will present at epsilon 0 energy level. And the other configuration, the second configuration, first particle will present at 0 energy level, second particle will present at epsilon 0 energy level, third particle will present at 2 epsilon 0 energy level. So the total number of the total energy of the system will become the epsilon 0. And similarly, in the next configuration, 2 particles will present in 0 energy level, and 1 particle will present in 3 epsilon 0 energy level. So the total energy level of the system, so the total energy of the system will become 3 epsilon 0 respectively. So these are the different configurations. It is important to note that the total energy of all the arrangements is the same as that of only difference in the distribution of energy over the particles. So the total number of microstates associated with a given configuration is known as weight of configuration and is represented by W. So if one in one configuration the number of microstates will be more, that will be represented by weight of the configuration, that is W. Now, so here you can see, so in the first configuration the weight is 1, for second configuration the weight is 6, the third configuration the weight is 3. So now a question comes that which of the possible configuration is likely to be observed the system at equilibrium, since all the microstates have an equal priori probability of being observed. The probability observed is 1, 1, 1, 0 configuration with maximum number of microstates. So here you can see one particle will present in 0 energy level, another particle will present in epsilon 0 energy level, and another particle will present in 2 epsilon 0 energy level, having the maximum number of weights or maximum number of microstates. So here in that case W will be 6. So that will be the maximum in the case. So the probability of observing this configuration is simply the number of microstates associated with the configuration divided by total number of microstates possible. So the probability of observing this type of configuration will be number of microstates for this type of configuration 6, total number of configuration 10. So the probability of getting this type of configuration will be 6 by 10, that is equals to 6, 0.6. So the 3 particles discussed above provides a general approach to determine the most probable configuration of the energy of a chemical system. That is, we work out all the possible configurations of energy and determine the corresponding microstates. The configuration with greatest number of microstates is the likely configuration. So if more number of microstates will be there, if the W value will be more, then the configuration is the likely configuration. Such an approach Such an approach is fine for the system with small number of particles. So if small number of particles, we can easily manually find out which configuration is the likely configuration. However, it is difficult task to do similar exercise for practical chemical system having astronomical number of particles, because for chemical system, if 1 mole of particles will be there, the number of particles will be 6.022 into 10 to the power 23. So it will be very difficult to find out, it will be very difficult to calculate the W value for such type of particles. However, it is difficult yet to do the similar exercise for in the chemical system. For such cases, we need to find a way. So, because as we are dealing with chemical system, so for 1 mole of chemical system means large number of molecules, that is large number of particles, that is 6.02 into 10 to the power 23. So, for such cases, we need to find a way to obtain the number of all the microstates associated with configuration without counting. So, here as in the what we have discussed in the previous cases, so as less number of particles there, just 3 and 5 particles are there, we can count the number of microstates or W values. But in case of chemical system, large number of particles are there, astronomical number of particles are there. So in that case, we have to find a possible way without counting. Fortunately, it is possible to work out an exercise for the same. So one question is there: what is the relationship microstate and configuration? So here this is the configuration, and these are the corresponding microstates. So the various the answer will it is clearly given the answer. You can see the problem in the hand is to work out the number of possible ways. So you can do the answer easily. Now coming to the problem in hand is to work out the number of possible ways of distributing n distinguishable particles, not indistinguishable or not identical, different particles. So we have to arrange n distinguishable particle among the different energy states epsilon 0, epsilon 1, epsilon 2 and dot dot. So here the problem is to work out the number of possible ways of distributing n distinguishable particles among the different energy levels epsilon 1, 0, epsilon 1, epsilon 2, epsilon 3 and so on. Such that there are n0, n1, n2, n3 and so on particles them respectively. To begin with, we assume that the given energy state can have only be a single particle. So now, since there are total number of n number of particles, we can assign an energy state to first particle in n different ways. So n number of particles are there and n number of energy levels are there. So for first particle, we can arrange the first particle in n different ways. Once an energy state is assigned to the first particle, so the next energy state can be assigned to one of the remaining particle. That means to the second particle. So for the second particle, the number of different ways of arrangement will be n minus one, because the first particle is already assigned, and similarly for the second particle, for the third particle, the number of ways to arrange is n minus 3, n minus 2 and so on. Thus, there are total number of ways of arranging n number of particles, n number of distinguishable particles in n number of energy states will be equals to n whole into n minus 1 whole into n minus 2 whole into n minus 3 and so on dot dot into 3 into 2 into. So the number of ways to arrange the last particle is 1. So that will become 3 into 2 into 1. So that is called n factorial ways assigning the energy state for n distinguishable particles. You'll recall from your earlier classes that chemical systems, all the particles, that means atoms and molecules, do not have the same energy level, and a given energy state can be possessed by many particles. So we know that the in the chemical system, that means for atoms and molecules, all the atoms and molecules do not possess same energy level, but a given energy level, many atoms and molecules will be present. You may likely to revisit Maxwell's distribution of molecular velocity that we have studied in gaseous state. It implies that more than one molecule can have the same energy. So, n distinguishable particles are so assigned to different energy states that N0, N1, N2, N3 particles respectively having energies epsilon 0, epsilon 1, epsilon 2, dot dot. And thus by considering that a given energy state can be had only be a single particle, we have overestimated the possible microstates. We need to make a necessary changes by correcting the overcounting of identical permutations. Since each N0 particles can have the energy equals to epsilon 0, there are N0 factorial different ways in which the distinguishable particles could have been selected to have the energy states epsilon 0. Similarly, N1 particles could have assigned energy epsilon 1 energy state, and the epsilon 1 energy state. So there are n1 factorial different n1 factorial different ways in which the distinguishable particles could have been selected with having energy state epsilon 1 and so on. Therefore, the total ways of distinguishable ways of distributing n particle in the different energy state are required. Regardless for the order of the particles were chosen, the weight of the configuration W equals to n factorial divided by n0 factorial into n1 factorial into n2 factorial into n3 factorial dot dot. So in the three particle example, so if we put the three particle example here in this formula, if we put the three particle example in this formula, in the three particle example, n equals to 3, and we can calculate the number of microstates for different configuration as given in the table number 1. So the number of permutations of each configuration for a system containing three particles with total, so three particles will be there, total energy should be 3 epsilon 0, and here we will find out the number of ways by this formula, not by directly counting what we have discussed in the earlier cases. So first one is configuration 1. So in the configuration 1, all the three molecules will present at epsilon 0 energy level. So N0 equals to 0. So N0 corresponds to 0 energy level. N1 corresponds to epsilon 0 energy level. N2 corresponds to 2 epsilon 0 energy level. So in the first configuration, N0 equals to 0, N1 equals to 3, and N2 equals to 0. So the number of permutations, number of weight equals to n factorial divided by N0 factorial into N1 factorial into N2 factorial according to this formula. This one, the total permutation or total weight W equals to n factorial divided by N0 factorial into N1 factorial into N2 factorial. So n factorial is 3 factorial divided by N0 factorial is 0 factorial, that is 1 because N0 is 0, and N2 factorial, that is 0 factorial, that is 1, and N1 factorial, that is 3 factorial. So 3 factorial by 3 factorial, that is equal to 1. So the total number of permutation or the total number of weight W value equals to 1 for the first configuration. And here the probability will be 1 divided by 10, W by 10. So that is 0.1. And in the configuration 2, in the configuration 2, N0 will be 1. So that means one particle will present at a 0 energy level, N1 will be 1, and another particle will present at epsilon 0 energy level, and N2 will be 1, another particle will present at 2 epsilon 0 energy level. So here the W value will be 3 factorial or n factorial divided by N0 factorial plus N1 factorial, again. So here the number of permutations or W value equals to n factorial divided by N0 factorial into n1 factorial into n2 factorial. That means 3 factorial divided by 1 factorial into 1 factorial into 1 factorial. So all the denominator will become 1. So 3 factorial, that means 6. And the probability will be 6 by 10, that is 0.6. And here in the third configuration, two molecules will present at 0 energy level and one molecule will present at 2 epsilon 0 energy level. That means N0 will be equals to 2, N1 will be equals to 0, N2 will be equals to 1, and W value is N factorial divided by N0 factorial into N1 factorial into N2 factorial, just applying this formula. So you can see here N factorial is 3 factorial and N0 factorial is 2 factorial, N1 factorial is 0 factorial, that is nothing but 1, N2 factorial is 1 factorial. So the numerator become 3 factorial, that is 6, and the denominator will become 2 factorial, that is 2. So 6 by 2, that is 3. The probability will be 3 by 10, that is 0.3. So what we have discussed by individual counting, same result we are getting by applying this formula. So this formula can be applied for large number of particles or molecules. So here you can see if you add the total probability, for the probability for configuration 1, that is 0.1, the probability for configuration 2, that is 0.6, and the probability for configuration 3, that is 0.3, the total probability will become 1, and here the total number of weight or the total weight will become 1 plus 6 plus 3, that is 10. And here the probability observing ith configuration is given by the weight of the ith configuration divided by total weight. Again, I am repeating the probability of observing ith configuration. The probability for ith configuration is given by weight of the ith configuration divided by total weight of the all the configuration put together. So the PI, probability of ith configuration, PI equals to Wi divided by W1 plus W2 plus W3 plus dot Wn, which is equals to Wi divided by summation of Wi from 1 to n. And if we do the numerical for the 5 particle system, what we have already done by individual counting, but if we apply the formula here for the 5 particle system, the number of permutations or number of microstates for each configuration for a system containing 5 particles with total energy 10 to the power 10 epsilon 0. So this question we have solved by individual counting, but here we will do the same question by applying the formula for W and formula for P. The first one is for configuration 1. All the 5 particles will present at 2 epsilon 0 energy level. So the total energy will become 10 epsilon 0. Now, the number of particles in the different energy state, that is N2 equals to 5. The number of particles in the remaining energy states are 0. So the number of permutations is total n factorial divided by n1 factorial into n2 factorial into n3 factorial into n4 factorial into n5 factorial. So except n2 equals to 5, but the remaining will be 0. So the permutations will be 5 factorial by 5 factorial, that is equals to 1. And the total probability will be 121. So the total number of configurations will be 121. Hence, the probability will be 1 by 121, that is 0.008. Now coming to configuration number 2. In the configuration number 2, so this type of arrangement of particles are there. One particle will present at epsilon 0 energy level, another 3 particles will present at 2 epsilon 0 energy level, and the fifth particle will present at 3 epsilon 0 energy level. The remaining 2 energy states will be vacant. That is N1 equals to 1, N2 equals to 3, and N3 equals to 1. The W value equals to 5 factorial by 3 factorial into 1 factorial into 1 factorial. That is 5 factorial by 3 factorial. So which is equals to 20. So the probability will be 20 by 121, that is equals to 165. I will get 121. So so here so if you add all the things 1 plus 21, 20 plus 30 plus 30 plus 20 plus 21, that will become 121. That is the total probability. And similarly, you can see the different probabilities of the different configurations what we have discussed in the previous same example manually. Here we are applying the formula, we are calculating the number of permutations or W value and the corresponding probabilities. So here if you add the probability, the total probability will become 1. So one question is there, another question is there. Consider a system consisting of 5 molecules which can occupy any one of the available energy state having energies equals to 0 epsilon, 2 epsilon, 3 epsilon, 4 epsilon and 5 epsilon. So that means 6 energy levels are there, 5 molecules are there. So the 5 molecule can present in any one of the 6 energy levels. But the condition is that if the total energy of the system is only 5 epsilon, calculate different possible ways in which the molecules which can occupy the various energy levels. So here we will apply the formula and do the numericals. So for distribution 1 molecule will be present at N5. N5 means the energy level is 5 epsilon. So, and the remaining 4 molecules will be present in N0. N0 means the energy having 0 energy. So the total energy of the system will become 5. And here W equals to, here the W equals to 5. W equals to 5 and the probability, here the probability is W, and in the second case configuration 2, 3 molecules will present in N0, 1 molecule will present in N1 and another molecule will present in N4. Here you can calculate the value of W, that is 20. You can calculate the value of W by applying that formula. Similarly, in the third configuration, the W value is 20. Similarly, for the 4th, 5th and 6th configuration, so these are the W values. The total W total is 125. So you can easily solve this question. These are very easy questions. The W total is 125, and if you find out the probability, probability will be W by W total. That means 5 by 125 equals to 0.04. Then 20 by 125, then 20 by 125, then 30 by 135, 125, then 30 by 125. So these are the probabilities of the corresponding configuration or distribution. And if you add the probability of all the configuration and distribution, if you add the probabilities of all the configuration or distribution, then the total probability will become 1. You can check that one also. If the total probability become 1, then your answer is right. So the possibility distribution and corresponding weights of probability for 50 molecules under same set of conditions. So 50 molecules will be there, but the total energy should be 5 epsilon 0. So, so the different configurations are like this. 49 molecules will present at N0 energy level having 0 energy, and 1 molecule will present at N5 energy level having 5 epsilon energy. And the second possible is that 48 molecule will present at 0 energy level, 1 will present at epsilon energy level, and another will present at 4 epsilon energy level. So the total energy should be 5 epsilon 0, 5 epsilon, but the number of molecules present here are 50. So W value you can calculate by using that formula. And similarly, these are the corresponding W values. If you find out the probabilities, and the last distribution is that 45 molecules will present at 0 energy level, 5 molecules will present at epsilon energy level. The total energy will become 5 epsilon 0, and here the probability will be maximum, W value will be maximum, and the corresponding so that you have to add this one, you will find this is W total, and the corresponding probability is W by W total, that is 0.67. If you add all the probability, that will become 1. Here the configuration 7 is the most dominant configuration with the probability 0.65. Now the question is, if 500 molecules are there having the same condition with that should be the total energy will be 5 epsilon 0. So here 499 molecule will present at 0 energy level and 1 molecule will present at 5 epsilon energy level. And the seventh configuration is 495 molecules will present at 0 energy level and 5 molecules will present at epsilon energy level. So in all the distribution, the total energy of the system will become 5 epsilon. So here the W value in the first case, so these are the W values of the second, third, fourth, fifth, sixth and seventh cases, seventh distributions. And here when the number of molecules was 5, the probability was 0.67 in the seventh distribution. But when the number of molecules will become 500, the probability will be 0.9608 in the seventh distribution. And similarly, if we increase the number of molecules to 1000, but the total energy of the all the molecules will become 5 epsilon 0. Same type of distribution will be there, but you will get the probability for distribution 7 will be 0.9802. So on the basis of the calculation given above, we note that as the number of molecules increases, the weight of the most probable configuration or probability of the dominant configuration also increases. For the above example, we conclude that as the size of the system increases, the weight I, the weight or probability of the dominant configuration goes on increasing. At a certain stage, the dominant configuration outweighs the rest of the configuration. That is the probability dominant configuration. That is the probability of dominant configuration is so high that the system predominantly exists in the dominant configuration. All the microstates having equal prior probabilities, these are equally probable. However, large number of them is being associated with most probable microstates, make them such more probable than the other possible microstates. In such cases, W becomes the number of microstates for a given microstate or configuration. So the energy distribution of the dominant configuration is known as most probable energy distribution. So in the real system, we'll deal with astronomical high molecules, that is n should be in the range of 10 to the power 22 or 10 to the power 23 of the particle. The available number of energy levels are also very large. From the above example, we say that in the real system, W for the most probable distribution will be so close to W total. So if large number of molecules are there, number of molecules will become more and more. You can see, so this is W total. If the number of molecules will become more, then then the probability will be more close to total probability, or the W will be more close to W total. So in the chemistry, as we are dealing with astronomical number of particles, that means the number of particles is in the order of 10 to the power 22 or 10 to the power 23. So in that case, the W of the W of the most probable energy distribution is very close to W total, and hence its probability is approximately 1. Thus, for a real system, we need to find the W total, which is almost same as the W for the most probable energy distribution. In other words, we need to find the distribution of energy amongst the particles of most probable state. So one question is that determine the possible ways of distributing 7 distributable particles among the 4 energy levels with energies 0, 1, 2, 3 quanta, such that the total energy will become 3 quanta. Easily you can do by applying the formula. Repeat the question in the exercise 4.2 with 100 molecules under the same condition. So in the example 4.2, first case 50 molecules are there, then 500 molecules, then 1000 molecules. But the question is, you have to repeat the same calculation using 100 molecules under the same condition and calculate the W by W total for the dominant configuration. And from this distribution, probability, and microstate concept, will go to derivation of Boltzmann distribution. So here I will take 2-3 minutes of gap, and after that again we will continue. So here We will derive the Boltzmann distribution, derivation of Boltzmann distribution. We have shown in the above equation 4.1. So coming to the equation 4.1, this is this equation, the equation for W, the expression for W, that is equation 4.1. So in the equation 4.1, the equation is like this: n factorial divided by n0 factorial into n1 factorial into n2 factorial into n3 factorial into, and so on. So we have shown above equation 1 that the weight of the configuration depends on the total number of all ni's in it. So to determine the dominating configuration, we need to find the value of ni that maximize the function w. So we need to find out the ni which is having the maximum w value. This can be achieved by varying the values of ni and looking for the values that corresponding to dw equals to 0. You will recall from your earlier classes that to determine the maxima of a function, we have to equate its first derivative to 0. So when maxima will be there and if you will take the first derivative, it will be 0. However, so if the curve will be like this is the maxima, and if you draw the first derivative curve, the curve will be, the corresponding first derivative curve will be like this. So that will become 0. However, in case of system with many particles, it is mathematically convenient to maximize the function ln w instead of w. So if many particle system is there, we have to maximize the function into ln w instead of writing only w. So it is so because firstly large values of n and the value of w will be very large, and secondly for ln w we can employ Stirling's approximation that we have discussed in the last class. Let us take the natural logarithm form. We know that according to the Stirling's approximation, ln w equals to, so here instead of taking only w, we are taking ln w, because for large number of particles it is better to take ln w. So ln w equals to ln factorial divided by ln ln w equals to ln n factorial divided by ln 0 factorial into ln n1 factorial into ln n2 factorial into ln n3 factorial, and so on. And here so here ln w equals to ln n factorial minus ln n0 factorial into n1 factorial into n2 factorial into like this. So again, we can find out ln w equals to ln n factorial minus ln 0 factorial minus ln n1 factorial minus ln n2 factorial, and so on. Putting ln I together, we can write ln w equals to ln n factorial minus summation of ln ni factorial. Now using Stirling approximation, for Stirling approximation what we have studied in the last class, because ln n factorial is equals to n ln n minus n. So this is according to Stirling's approximation, what we have studied in the last class. So putting the value of ln n factorial by using Stirling's approximation, we can write ln n ln n minus n in place of ln n factorial applying Stirling's approximation. And again, we know that summation of ni equals to n, and hence we can write the expression ln w equals to ln w equals to n ln n minus n plus n minus summation of ni ln ni. That is, so n will be cancelled out. So the final value will be n ln n minus summation of ni ln ni. Now let us note that a change in the configuration of the system is accompanied by the change in population of each of the state I from Ni to Ni plus Dni. So the corresponding change in ln W can be, so now if we take the derivative dln W, that will become 0. The term in the right hand side gives the summation of the total rate of change of ln W with Ni multiplied by total change Ni dni. For ln W to be maximum, this sum must be equals to 0. So far, we have considered all the states of the same energy, implying that the configuration have the same total energy. Let us extend the argument now into different states having different energies, epsilon 0, epsilon 1, epsilon 2, and so on. Since an isolated system has a constant total energy, so we can retain only those configurations that have the total energy, and the configuration must satisfy the following condition, and the condition is summation of ni epsilon I equals to E. In other words, one particle one particle in the collection is free to gain or lose energy, but a corresponding amount of energy must be decreased elsewhere in the system. Thus, the following condition should hold, that if summation of epsilon I dni equals to 0. So this is equation 11, and the previous equation is equation 10. Now the equation 11, 12 represent the energy constraint on the system. Now, since the total number of particles n of the system are fixed, we cannot vary the population of all the energy state independently. A change in population of any state must be accompanied by corresponding changes in the population of the other state. That means if the population of one state will be increased, then the population of the other state must be decreased, because the total number of particles will be constant, that is capital N. Mathematically, the summation of Ni equals to n. It demands that the sum of all the changes of dni must be 0, because the total number of particles will be 0. So this is equation 13. And this one is equation 12. The summation of total number of particles equals to n. Now the equation 12 and 13 represent the number of constraint of the system, and thus the probably reduces solving the equation 4.9 under constraint as given in the 11 and 13. So for this we will use the Lagrange method on determined multipliers discussed. So that will be discussed later. So to rewrite equation 8, we can write ln W equals to n ln n minus summation of nj ln nj. So by labeling the number of states by j in place of I, we can write this one. Now differentiating with respect to ni, we can write dln W by dni equals to dn ln n by dni minus summation of nj ln nj by dni. Now solving the terms in the right hand side using different differentiation by parts, derivative by parts. If we use derivative by parts, we can solve the RHS, and here we will take the total number of particles will be n, and nj is independent upon ni. So nj is a particular the number of particles in a particular state. So in the differential we will finally will, so by simplifying the differential, we can write ni equals to n e to the power alpha e to the power minus beta delta I. This equation is the mathematical form of Boltzmann distribution. It gives the number of molecules in the ith energy state of a dominant configuration. Again, I am repeating, this equation 35 is the equation. So that is the mathematical form of Boltzmann distribution, and it gives the number of molecules in the ith energy state of the dominant configuration. Now Ni by n also equals to probability of occupation by the given energy level. To appreciate the significance of equation 35, this one, we need to determine the unknown multipliers, that is the coefficient alpha and beta. So we need to know what are the value of alpha and beta. First one is determination of alpha. We know that the sum of the populations of Ni of the states is equals to total number of molecules, that is N. That means the summation of Ni equals to N. That means the total number of particles or total number of molecules will be N. And from the Boltzmann distribution and from the mathematical equation of Boltzmann distribution, we can write summation of N e to the power alpha into e to the power minus beta delta I equals to N. Simplifying and cancelling N both sides, we can write, so this term will be out of the summation. So N e to the power alpha summation of e to the power minus beta delta epsilon I equals to N, and here we can solve like this, and the partition function, applying the partition function, so we can apply q equals to this. In order to solve this, we can apply q equals to summation of e to the power minus beta epsilon I. So this gives rise to pi equals to ni by I. So this is the probability of ith configuration, pi equals to number of molecules in the ith configuration divided by total number of molecules, that is ni by n equals to e to the power alpha into e to the power minus beta epsilon I. So that is equals to e to the power minus beta epsilon I divided by q. So this equation 40 is an important result. It quantifies the probability of occupying given energy of the dominant configuration of the energy. This well known, and the important result referred as Boltzmann distribution. And comparing equation 40, the expression of probability involving discrete variables. So the probability of xi equals to fraction of I fi divided by summation of fj from j equals to 1 to m. Now coming to determination of beta, and again we are repeating the same equation and taking the differential form. We can write this, and after solving we can find out the value of beta. Beta is nothing but, that is the proportionality sign. So removing the proportionality sign, we can write beta equals to 1 by kt, where k is known the Boltzmann constant, and having the value 1.38 into 10 to the power minus 23 joule per Kelvin. So the Boltzmann distribution equation 40 can be written as ni by n equals to e to the power minus epsilon j by kt divided by q, or ni equals to n by q into e to the power minus epsilon j by kt. So the denominator of equation 61 is termed the particle partition function or molecular partition function, and here ni equals to n into e to the power minus epsilon I by kt divided by summation of e to the power minus epsilon I by kt. So here the probability of its occurrence is proportional to e to the power minus epsilon by kt. Here T is the system's absolute temperature. In Kelvin scale, K is the Boltzmann constant. You may note here that at a given temperature, since the energies of all the levels are positive, K also have a positive constant and T is always positive. So now coming to the example. So in the example 4.3, you can see a molecule can be any one of the two states. Again, I'm repeating, a molecule can be in any one of the two states. What are the two states? Its excited state is separated from the ground state by amount of energy 8 into 10 to the power minus 21 joule. If the ground state has the energy 0, calculate the fraction of molecule in the excited state at 300 Kelvin. Now, according to the Boltzmann law, we know that Ni divided by N equals to e to the power minus epsilon I by kt divided by summation of e to the power minus epsilon I by kt. So this is the mathematical form of Boltzmann distribution law. Now let us first calculate the denominator by substituting the exponent. First we will calculate the value of the denominator, and after that we will solve that one. So, in the mathematical form of Boltzmann distribution law, the denominator is summation of e to the power minus epsilon I by kt, which is equals to e to the power 0 plus e to the power minus epsilon I by kt, that is equals to 1 plus e to the power this one. So, here we are putting the value of uh, epsilon 1. Here putting the value of epsilon 1, the value of epsilon 1 is 8 into 10 to the power minus 21 joule, already given. So the energy level of the first excited state divided by k kt. Here in place of k we put the value of the Boltzmann constant, and the value of t is there. So solving this, we can write this, the denominator will be 1.15145, and similarly the numerator will be 0.145, and hence Ni by N equals to 0.127. So the fraction of molecules in the excited state at 300 Kelvin will be 0.127, that is about 12.7% of the molecule will be in the excited state at 300 Kelvin temperature. So by applying the Boltzmann distribution function, we can solve. So, so here one long question is derivation of Boltzmann distribution function, determination of value of alpha, determination of value of beta, and some numerical questions will be there. The numerical question will be like example 4.3. And after that we will discuss molecular partition function. So here we will discuss the molecular partition function. That relates the properties of the molecule to the microscopic properties of the system. As discussed above, the partition function is mathematically defined as, so here the partition function is Q equals to summation of e to the power minus epsilon I by kt. This gives the sum over all the energy states in the Boltzmann distribution. And here, so recall the Boltzmann distribution gives the distribution of molecule over different energy levels of in the dominant configuration. Therefore, the partition function is also known as molecular partition function. While considering the Boltzmann distribution, we had assumed that the discrepancy of all the energy levels is 1. However, since the molecules have many degenerate energy levels, it is important to include the degeneracy of the expression of for partition function. Therefore, the molecular partition function can be written as Q equals to, instead of writing this, we should write Q equals to Gi into Q equals to summation of Gi into e to the power minus epsilon I by kt. Here Gi is the discrepancy of the ith energy level. And we know that the total energy of the molecule has the contribution from the translational energy. So it is, we know, so this is called Born-Oppenheimer. This is called Born-Oppenheimer approximation that we have studied in the graduation level. That the total energy of the molecule has the contribution from the translational energy, rotational energy, vibrational energy, and electronic energy of the molecule. That means the epsilon I total equals to epsilon I trans plus epsilon Y rot plus epsilon I vibe plus epsilon Y EL. So this is the energy contribution due to translational energy. This is the contribution due to rotational energy. This is the contribution due to vibrational energy, and this is the contribution due to electronic energy. And according to the Born-Oppenheimer approximation, this energy can be taken as independent of each other. That means any term of energy is not dependent upon one another. Is not dependent upon other. Thus, the molecular partition function without considering the degeneracy can be written as Q equals to. So this is the partition function. If we put this value in the partition function equation without degeneracy, considering the degeneracy, the molecular partition function can be written as e to the power minus, in place of epsilon I, we can write epsilon Y translational plus epsilon Y rotational plus epsilon Y vibrational plus epsilon Y electronic divided by kt, or Q equals to summation of e to the power minus epsilon I translational divided by kt into epsilon e to the power minus epsilon I rotational by kt into e to the power minus epsilon j vibrational by kt into e to the power minus epsilon I electronic by kt. Now separating each term, introducing degeneracy of each type of energy, we can, so if we put the degeneracy, we can write Q equals to summation of Gi translational into e to the power minus epsilon I translational by kt into summation of Gi rotational into e to the power minus epsilon I rotational by kt into Gi vibrational into e to the power minus epsilon I vibrational by kt into Ei electronic into summation of Gi electronic into e to the power minus epsilon I electronic by kt. Thus, the total partition function is the product of partition function of each type of energies of the molecule. This is known as fractionalized partition function. We can calculate the contribution of each type of partition function of the total partition function separately, and put together to get the total partition functions. Let us learn how to calculate the partition function of each type of energy. So we know that the different types of so according to the different types of energy contribution, the different types of partition function will be translational partition function, rotational partition function, vibrational partition function, and electronic partition function. So first we will calculate the value of translational partition function. We know that the energy of nth level due to translational partition function, that is epsilon n trans equals to n square h square divided by 8 ml square. So this is due to translation of a molecule from one place to another. Here n is the quantum number, and the energy of the lowest energy state, that is the ground state, n equals to 1, and epsilon n translational equals to h square by 8 ml square. In case of Boltzmann distribution, the energy of the lowest energy level is taken as a 0. Therefore, the energy of the nth energy level must be scaled relative to the lowest energy level. This implies that the energy of the nth energy level relative to the lowest energy level equals to epsilon n translational of the nth energy level. So here that is equals to n square minus 1 whole into epsilon 1 translational. So the translational partition function in the x direction can be written as qx translational equals to summation of e to the power minus n square minus e to the power n square minus 1 whole into epsilon 1 translational divided by kt. And similarly, qx translational is equals to integration of e to the power minus n square minus e to the power minus n square minus 1 whole into e1 translational divided by kt dn. To solve this integral, we use the approximation that n square minus 1 is equals to n square. It's similar to n square, and the lower limit of the integral change to 0. Therefore, the value will become like this. Now let us substitute in order to solve this one, we should substitute this one as x square, and differentiating and simplifying, we can write dn equals to this one, and substituting the values, we can find out the qx translational like this. So the integral of the standard form, and finally on the simplification, after simplification we get qx translational equals to 2 pi ktm divided by h square square root of 2 pi ktm divided by h square into L. This is the expression for translational partitional function in x direction, and in the similar way we can calculate the translational partitional function for y direction and also for the z direction, and hence the total translational partition function q trans equals to summation of its contribution from the x, y and z directions. So the simplifying, we will get the q trans value like this, that is q trans equals to 2 pi ktm divided by h square to the power 3 by 2 lbh. So length, breadth, height, and the total multiplication will give rise to v. So v is the total translational partitional function. So this is the total translational partition function, that is q trans equals to, so here q trans equals to 2 pi ktm divided by square to the power 3 by 2 into v. And so here one question is there. 1 mole of neon gas occupies a volume of 0.0245 meter cube at 298 Kelvin. Calculate the translational partitional function of the system. So if the question will be like this, we have to the translational partition function is given by the following expression, that is q trans equals to 2 pi ktm by h square whole to the power 3 by 2 into v. And most of the parameters are given or known. However, we need to calculate the value of the mass of the neon atom. So we will find out the value of m value for the neon atom. Mass of the neon atom equals to molecular mass divided by Avogadro's number. So its molecular mass in form of kg per mole, and its Avogadro's number, and we will find out the mass of a single neon atom 3.351 into 10 to the power minus 26 kg. and putting all the values in this expression, we will find out Q trans equals to this one. Now coming to the rotational partitional function. The rotational partitional function, in the similar way we can solve the rotational partitional function, and we will find out the value like this: Q rotational equals to 8 pi square IKT divided by h square. And similarly for the vibrational partitional function, we can calculate Q vibrational equal to 1 by 1 minus e to the power minus h nu by kt. And similarly solving for the electronic partition function, it is given by the expression Q electronic equals to summation of Gi electronics into e to the power minus epsilon I EL by kt. So the energy of the degeneracy of the first three electronic state of an atom from the first period is given as like this. So calculate the electronic partition function at 300 Kelvin. So by putting this value, we can find out the electronic partition function. Now coming to the next one is canonical assemblage. In the previous section, we have discussed the statistical treatment of a single system, which is the collection of many identical particles. A system is also known as assembly. A group of collection of assemblies or system known as ensemblage. So we had considered the total energy system to be fixed. However, in case of ensemblage, the energy of the system in contact with the surrounding of the fluctuate. So here, since the different part of the ensemble can be exchanged energy with each other, the energy of the ensemble will fluctuate. So in such cases, we cannot assume that the energy is fixed. However, we can fix the temperature and ensemble by keeping the contact with a large heat reservoir. The word canonical means according to the rule, the ensemble, which is the rule number of molecules, in which by rule the number of molecules n, volume V and the temperature T are kept constant, are known as canonical ensemble. So the total number of particles in the ensemble is n. The number of particles in an ensemble with energy Ei equals to Ni, and the weight of the configuration of the ensemble population N0, N1, N2, N3 like this. So similarly W of the ensemble, so that is the canonical distribution, and after that we can find out the E bar is the constant, that is N bar also fixed. So all these values will be fixed, and that will give rise to Q is the canonical partition function. Now the relation between molecular partition function and canonical partition function. So here the relation will be like this: Q equals to capital Q equals to Q1 into Q2 into Qn. For a distinguishable molecule of the same times, the molecular partition function will be same. Therefore, Q equals to Q to the power n for distinguishable particles. When the particles are indistinguishable, the above expression is modified as Q equals to Q to the power n divided by n factorial for indistinguishable or identical molecules. Now coming to thermodynamic properties and partition function. So here the average energy of the molecule. So this is the average energy of the molecule equals to E divided by N. And that will give rise to, and we know that Ni equals to N e to the power minus epsilon I by kt whole divided by k. Therefore, the average energy equals to this one. Using the mathematical arrangement, we can write this. Therefore, the average energy equals to dlnq by dlnq by d beta. So the average energy equals to epsilon 0 minus dlnq by d beta at constant volume. So here some questions are there. Define the following microstates: weight of a configuration, dominant configuration, all these things are there. and already we have discussed. Consider the distribution of 5 quanta of energy among the 3 distinguishable particles having 4 variables. All these type of questions we have also solved. Give the constraint applied to the Boltzmann distribution. That means the conditions applied to the Boltzmann distribution. Which among N2 and H2 will have the higher translational partitional function? Translational partition function, just you will put the mass of one molecule of nitrogen or hydrogen and we will find out that one. Calculate the electronic partition function at 300 Kelvin for a system using its first 3 doubly degenerate energy levels with energies this 1, 2 and 3rd energy level. Then the rotational temperature of HI molecule is this one. Calculate the moment of inertia I for HI. So here are the solutions of the above questions. All these things we have discussed, and here some terminal questions are there. That is also the solution. Okay, so we will stop here.